Hi everyone. Hello again. Looks like I aged that I don't see you. We are going back to Mapse for his third lecture to solid state detectors. So thank you very much again for having come here to give these lectures to us.
Thank you.
And please, again, feel free to make your questions. The materials of the lectures are available on the link, in Google Meet link, and the attendance list is going to be available by a link as well. Okay? So you can start. Thank you very much again for being here with us. See you soon.
Thank you. Good morning, everyone. Good morning outside as well. So today is the last lecture concerning the detector details, and I'm going to talk a little bit about the solid state technologies. And first, let me introduce you what is a solid state. When we think about solid state, we always think about semiconductor devices. Okay, always the same, because that was how they called this in the 50s and 60s before. And when think about semiconductors, we think about electronic components that are based on semiconductor materials such as silicon and germanium. For example, we have diodes, which are the most used semiconductor devices that we can use these guys for converting AC current in DC current. And we use transistors a lot, of course, that we can use for power supplies, for switchings, and also we know the drivers. We use SSD devices, solid state devices. That's why we call SSD, and we know that we have fast computers thanks to these guys. And also, on top of all these applications, we have also the particle detectors that are based on the same technology, semiconductors. This is an example for a PIX detector at CMS. I'm going to show this by the end of the lecture, and we will understand how this guy works and why we use this kind of technologies in particle physics. Sorry. Okay, some basics about the detectors. They were developed after the gaseous detectors. If you remember yesterday, the gaseous were developed by 1928, while this kind of technology was a little bit after. And here, particularly, we will be studying the silicon detectors, not with germanium, but only silicon. It's possible, of course, with germanium, but today I will just talk about the silicon detectors. And for measuring, we can use these guys for measuring photons and charged particles as well at our experiment, as I will show in the following slides. And we can use these guys to make precise position and time measurements, and also we can do some measurements of energy, but the main goal for these guys today in high energy experiments is for measuring position and time. And at the CMS, for example, we use a lot silicon strip detectors, really strips. And we use for particle tracking. We can see the tracks of the particles, and also we can identify the type of the particles, if it's a kaon, etc. And this is how we do at the CMS. This is the tracker of the CMS, and as you can see here, we have many modules, as you can see on this picture on the right. So each of these modules, it has a lot of strips that are very segmented inside the detector. And then what is important here is that due to the miniaturization of the electronics, we have a very nice precise measurements than before, right? So as yesterday we saw about the gaseous detector, we can compare the two technologies, so we can make a comparison to understand better the main differences between them. For example, if we take a gaseous detector and the medium is composed of a gas, right? While in this case of the semiconductor, we put in the medium the semiconductor material. Okay, we will understand what is this in few slides. And in the gaseous detector, when a particle passes through it, we produce a pair of electron and ion. While in the semiconductor, we produce also a pair, but now it's electron and a hole. We will see what is this hole as well. Concerning the DEDX, at the gaseous detector, there is a low stopping power, low DEDX, and the semiconductor is high. okay? And another difference is that normally gaseous detector, they are bigger, they are very large, while the semiconductor, they are compact. We will see a picture that it shows the difference between the two of them. And also the last is that the gaseous detector, they have low cost. To build big detectors, the cost is not that much, but unfortunately for semiconductors, the cost is very high, okay? And the main advantage concerning the type of ionization that we produce inside this detector is that to produce a pair in this guy here, we use 10 times low energy than a gaseous detector. It means that we don't need a very energetic particle to create a signal. So we have a more sensitivity than a gaseous detector. That's why I talked about sensitivity yesterday. Okay, first of all, we need to know some notions of semiconductor physics. I don't know if you know about this kind of physics, but normally people don't see this during the graduation. But I will try to explain the main basics so we can understand how we can use this kind of technology to detect particles, okay? So, first, a semiconductor material is a crystalline material. It means that it has this periodic arrangement of atoms inside the material. It's like a crystal, okay? And we can define for understanding this a thing that is called energy band structure. What is this? This is a structure that is divided in three things. We have the conduction band, valence band, and we have an energy gap between these two bands. The conduction band is the highest level of energy in the insulator, semiconductor, or metal. And in the conduction band, the electrons are free to move, okay? While in the valence band, the electrons are bound to the atoms. In this case, they are not free to move as they are bound. And then we can compare three different types of material to understand these three concepts. First, if we take an insulator, we have a very well defined the valence band here. We have a very large energy gap between the valence and conduction bands. And in order to take an electron from the valence band where it is attached to an atom, we need to provide an energy greater than 6 eV in order to make this guy to the conduction band so we can make it free, okay? In metals, this is not true because our electrons are free to move. We know this, that in the metal this is basic. However, in the semiconductor, we have like the same formation as an insulator, but the energy gap is lower. You see that is 1 electron volt in medium. So to make a electron from valence band to conduction band, we need a lower energy, so we have more current than an insulator and then less current than a metal. This is basically the notion of semiconductors. And so the next concept is about the charge carriers. Imagine we have a semiconductor and we provide some energy to the electron on the valence band. When this electron takes some energies, it can move to the conduction band. And then when this electron goes up, it leaves a hole, a positive charge here. This is the hole, okay? In turn, another electron that was below can occupy this hole. And then you see that the electrons are moving up to the conduction band and the holes are moving down. They are not really moving down, but the electrons are moving and the holes are apparently moving down. So we have two charge carriers in the semiconductor. We have the holes that are apparently moving down in the valence band, and we have the electrons that are moving up towards the conduction band, okay? And remember that in silicon, we have 4 electrons in the valence, okay? In the valence of the silicon. And therefore, we have 2 charge carriers. We have free electrons and we have holes. So these are the holes. In this case, they are positive charges. Okay, now 3 more definitions that we can take approach. The first one is that at equilibrium, we have the same numbers of electrons and holes. and this we can calculate from the Fermi-Dirac statistics using this equation here. And I leave this as an exercise for you as well. And this mainly depends on the temperature of the material and of the energy gap of the material. For example, if you take a silicon at 300 Kelvin, we have more or less 10 to 22 atoms per cc. And if we calculate the Ni, we got this value that is equivalent to a very high resistivity of the material. And this means that out of 10 to 12 atoms, we have one atom ionized, which is very low, but this is what we have in this kind of materials. That's why we need to do something that I am going to talk in the next slide. And also remember yesterday that we talked about the drift movement of electrons, okay? Remember, drift movement is when we have an electric field, so they can accelerate by using this electric field. In the end, you will see that the same principle for the gaseous detector for moving the charges is the same used for the semiconductor devices. And on top of this, we have a recombination and trapping. I just say that the electrons, when they provide energy, they move up to the conduction band. However, due to some impurities of the crystal, they can recombinate with the holes, and then they can emit electrons. But this is a problem because it can reduce the detector resolution. That's why we require that these crystals, they must be very, very pure in order to avoid this kind of problem in this kind of detectors, because this is a huge problem, because we want a very nice resolution. If we cannot provide, so that's no way to make detector with not pure crystals. Okay, we're almost there. Now the last step before understanding how we can use these guys for detectors is the concept of doped semiconductors. Normally, in a pure crystal of semiconductors, the number of electrons is equals to the number of holes. However, we can take impurity, and then we can add in this material to get one more electron or one more hole. How can we do that? We take, for example, we know that the silicon is tetravalent, it has 4 electrons, but we can dope this guy with either a pentavalent or 3-valent atoms. And then we have 2 possibilities. The first one is the N-type semiconductor. In this case, what we do, we take a pentavalent atom, it means that it has 1 electron in excess, and then we put inside the silicon. And then this causes an excess of electron. That's why we call N-type semiconductor, N of negative, right? And then this will increase another, it will introduce a new level inside this gap here, where the difference between the conduction band and this level is 0.05 electrovolts. It's very low. So it's easier for us now to move the additional electron to the conduction band. So we enhance the conductivity. That, if you remember, it was very high due to this high resistivity of the material. Okay, and then we can do the same by using a 3-valent atom, and then this is the p-type semiconductor, YP, because we put a positive or a hole inside it, right? So we have 2 possibilities. We have the N-type semiconductor and the p-type semiconductor. And what if we take NP and a p-type and put them together? What we would have? We will have the NP semiconductor junction. That is the guy that we use for making diodes, transistors, and also particle detectors. Okay. When you do this, it's not a matter of simply putting them together. We have a technique, special techniques with engineering, with very difficult things to do to put them together. It's not a matter of putting them together. Anyway, this region that we can put here, we will, at the beginning, before the equilibrium, we know that we have an excess of electrons here and an excess of positive holes here. Due to the diffusion, the electrons will go to the other side and will recombine with the holes here, while the holes in this region will move towards the N region. And then after some times, they will stay in constant equilibrium and will create an electric field due to the negative charge and positive charge. So there is a potential now here, because they move and then they change the places. Because of this potential, we cannot have more charges moving. They need an additional energy to pass this potential. And this region is called depletion zone or space charge region. And this is the place that we use for producing signals for the particle detectors. Why? Let's say a particle passes through this guy here. It can knock out again electron and holes, and then we can accelerate them to create signal, and then we can detect, just as a gaseous detector. This is more or less what is happening here, right? And for do that, we need to increase this region in order to have a volume that we can detect particles. How can we do? We do the most common type of technique is the reverse bias diode. We simply take a potential, a voltage, a power supply, and then at the P region we put the negative voltage, and we see that the holes will be attracted to the right, while we connect the positive part of it here, and then the electrons will move towards the positive region, and then we see that the depletion zone will increase. Now we have a larger depletion zone or space charge region, and then we can use this zone for particle detection. This is how we can use these this technology for detecting particles. It's nice because it's the same technology for producing diodes and electronics. It's very interesting, this. And in practice, how can we do this? We just connect a potential to the N part, and then we can put the negative or grounded to the P layer, and then we have a sensitive volume, just a gas detector. If a particle passes here, it will produce a pair of electron and ion, and not ion that holes, and then we can detect the signals. Okay? And remember that I show you that the gaseous detectors are very huge. In this case, we have a very tiny detector at the order of micrometers. So we can have a lot of detectors, and then the precision is way, way better than before. And also we have very nice properties, because now, as I commented before, we need a very low energy to produce a pair. So we have more sensitivity than before, than a gaseous detector. We have good resolutions, because this is a very tiny detector. And then also we have a very precise position measurement using these guys. So this is what we have, let's say, with more modern detectors of particles today are based on this kind of technology. Okay, and that's why we can detect particles from the decays of Higgs bosons, of Z bosons, and etc. I'm going to show how this works at the CMS. Okay, just a comment about this. We can develop, using this reverse bias diode, several different detectors. The most common example is the silicon strip detectors, where we can have 2D detectors, and you can see these are the strips here, and also a 3D detectors, where we can have the strips. You see, we connect several tubes in the strip, and then we have the strip, and also we have pixels. When we are measuring pixels, we take each tub individually, this N plus and the P plus. Just a small comment about this. Okay, one of the types of these semiconductor detectors are the drift chambers. So we kind of merge the drift of the electrons using a silicon strip technology. How can we measure particles using this guy? We have here this is the depletion zone, and then when a particle passes through it, it will knock out electrons and then knock out holes. And then we have several strips which are P plus. And remember, at the P we put the negative potential. So electron will not go to the P because it's negative. Instead, it will go to the N plus, which is connected to the plus potential, and then we can detect the electrons, and then we form the signal here. And then we know by design the drift velocities of the electron. If we know the drift velocities in the time that they arrived here, we can measure the positions where they were collected. And then if we know the dE dx of the material, we know how much of energy it was deposited inside when a particle passes. Okay, we can use this kind of detector to measure the position with a very, very nice resolution, and also energies. But the best detectors that we can build using this technology are the silicon strip detectors. They are the most common detectors today for this kind of technologies. And as I mentioned before, the main advantages of it is that we can have very precise measurements at the order of micrometers, which is very nice for us, and also with a very high particle heights. We can measure heights at the order of a megahertz, which is incredible as well for today. And sometimes we can have strips with its own electronic signal, which is also very nice because of the miniaturization of the electronics. And depending on the type of the measurements, we can measure several strips in one electronic, or we can take one signal per each strip. And this will vary of our application, if we want high height, if we want low height, that will depends on what we want to measure. Basically, at CMS, we have two kind of silicon detectors, the silicon strips and the pixel detectors that I'm going to show in a few slides. Also, we have the possibility of adding a X and Y measurement, so we can make a 2D measurements with a single detector. We simply do by adding strips in this direction, the N plus, and the strips on this direction, and the P plus. And then if a particle passes here, we can have the information in X and Y, so we can build precisely where the particle passes. And this is what we do at the CMS. We precisely know where the particle is passing. And as before, the measurement precision is that at the order of micrometers. We can achieve down to 2 micrometers. This is really impressive. However, because of the way we build the silicon detectors, putting some layers to protect the detectors, due to the high flow, we need to guarantee that the detectors is well constructed with very pure crystals. Otherwise, as the time passes, the detector will die. So we need to guarantee that the detector is well constructed with low impurities. And before in 50s and 70s, that was a very huge problem, but today we are in the state of art of this development, so this is not a problem anymore. But always when we think about the future, we remember that we are going to increase the luminosity of the LHC, so we need to test the detectors beforehand and to see if it can handle very high particle flows, because we need to guarantee that after 20 years, 30 years, it will continue working well with high efficiency, right? And there is a thing that happened in 2016 at CMS. One of these modules in a very specific place of the detector was damaged due to the radiation. So we had to stop the run, and then it took like 2-3 months to fix the detectors, and then we stopped taking data. So this is a very sensitive problem that we have because of the high flow of radiation. So, okay, now let's talk about a little bit CMS, and then the applications of the silicon strips and silicon pixels detectors. So I don't know if you are familiar with the CMS, but this is experiment here, where I always like to show this person here to compare with the size of the detector. And the CMS is a general purpose experiment. It means that we can measure all kinds of process in the standard model, and also we look for physics beyond the standard model. And together with Atlas, CMS and Atlas, they discovered the Higgs boson using common data in 2012. And basically, this is how it is. It is 21 meters in length, 15 meters in diameter, and we have several different detectors here. And also there is this solenoid magnetic that we have here on the center. And do you know why we have this magnet? No? Yeah, basically this. Because we have charged particles traveling, and then we bend the trajectory, and then we can measure the momentum. It's basically this. And then we have many subdetectors. Starting from the center, we have the tracker system, which is composed of silicon detectors. First, we have the pixel, and then just after we have the strips. Okay. Then after that, we have the calorimeters. We have two types of calorimeters. We have the calorimeter that are measuring the electromagnetic calorimeters, and then we have the hadron calorimeters. And then just after, in the outermost part of the detector, we have the muon system, which is entirely based in gaseous detector. Okay. For example, we have the cathode strip chambers. They are detectors that are also gaseous detectors. They are here on the end cap region. We have the drift tubes. They are on this part of the detector here and here, which is the barrel region. And we have the resistive plate chambers, RPCs. They are in both end cap, all over this region and all over this region, the barrel. And we have the GENS, gas electron multipliers. If you remember, this was the detector that we saw the simulation yesterday. They are here, and they are new. They were installed in 2019. They are very new. And let's say we want to measure, for example, a Higgs boson decay into 2 photons. What would you do to do this? We take, for example, this part of the CMS. You see, we cut, and then we have this drawn. This is the photon. See, so photon will be measured. We will leave tracks in the silicon detector here, on the pixel and on strips, and the photon will die here on this place on the electromagnetic calorimeter. And then if we want to measure a Higgs boson, we can take 2 photons. We can analyze the data of these 2 photons. We can reconstruct the trajectory and see if it comes for the same place, for the same vertex. And then we do some statistics analysis to see, that 2 photons are really for a Higgs boson or for another event. So we have some techniques to identify this. This is a kind of analysis that we do, and it's very important because we need the information for the tracking system that are used by silicon detectors. And then that's why you need a very precise position measurements here. Because imagine that the flux of particles here, that when they collide, is like 600 million of particles passing in 1 second. So we really need these detectors. Just a little bit of water. Yeah. Microphone.
This tracking system uses the ionization of the charged particle, which is curved by the magnetic field. Is this to reconstruct the path?
Could you repeat, please?
If this tracking system uses the ionization of the particle to reconstruct the path.
Yes.
It's basically this.
Yes.
And the particle dies in the calorimetrics, for example, just to know which kind of particle it is, to identify this particle.
Yeah, because basically we have this we have these electromagnetic calorimeters, so we don't put the photon to go further this. We know that it will die there, and then we on top of this, the photon will not generate signal in the other detectors, because in the end we want at the end of the CMS only muons, because we have a lot of physics that we can learn from muons. That's why we put calorimeters to kill here photons and here to kill hadrons. Imagine that we don't have this hadron calorimeter. What would happen? Kaons and pions would pass through the system and would generate signals in the muon stations, which doesn't make any sense because we want muons there. But you know why we want muons? Because, for example, we can measure the Z boson decay into 2 muons. So if we let kaon and pions go there, it will be a huge background for us. Okay.
So one last question. So the moment of the particles you calculate using the tracking system, and the energy you measure using the calorimeters. Is this, or you use both for the
yes.
both process?
Energy is with the calorimeter, but also we know more or less the information from the silicon. We can measure a little bit of energy, because imagine we have a pion. Pion was produced here. It will leave tracks on the silicon system, and it will lose energy. So we need to take into account this energy as well. Okay? No problem. Yes?
So, Maps, I apologize if my question sounds very obvious,
No problem.
but I want to know if you said before that we can do the experiments. There's a lot of particles, million particles, and if I want to know if it's possible to this detector to detect, for example, a boson among other particles. And when you mentioned the tracker system, I want to know if it's also possible to measure the trajectory of the particle with precision. So if you can detect where it would be at that specific time and to make a pass away from the process, of is this not possible to
So the question is if we can measure with the precision a track.
yeah, to make a pass.
Yeah. We can. We have all the signals recorded, and this goes to a computer, to a data analysis system, and then we have all data available, and we know precisely where it came from. So we can precisely reconstruct the track.
Oh, okay. Even if the particle is among a lot of particles with different aspects of characteristics.
Yes.
Oh, amazing. Thank you.
And sometimes we cannot, for example, at CMS, we cannot distinguish between KO and PIO only with the measurements. We do some statistics to discriminate between them. Okay. And what I want you to learn here is that we cannot directly measure Z bosons, Higgs bosons, because they are not seen by the detector. Because Higgs bosons is created, and just after it disappears and decays into, for example, muons, leptons, and so on. Okay, and then we measure basically the state, the final states, which are muons, photons, hadrons, kaon, pion. Okay, that's what we do. Electrons, and also from the hadron calorimeter, we can measure with not directly neutrinos, because we reconstruct the event, and then we see there is a energy that is missing here, and that this energy, which is the missing energy, is related to the neutrino. But we have a lot of analysis tools with statistics to precisely confirm that this is due to a neutrino. Okay, this is what we do. Sure, you can ask.
Where's the solenoid there in the picture? Is
It's here.
okay? So after the hadron calorimeter, right?
Yeah, and see, this is the field is coming from there to here, and it is like this. You see, there is the dot, the cross. The field is like this.
Okay.
That's why we see that at the beginning the particle is like going like this, the muon, and then it changes the direction because of the field changes the vector.
So there are like two.
No, because
Or
it goes like this, a solenoid. If you take the high and hole,
Mm-hmm.
you know, it is like this.
Oh, okay. So you're saying that the magnetic field is in one direction is inside, the other direction
Yeah,
outside
yeah.
because of the
Because it's
solenoid.
like this, and then if you do the
Okay.
high and hole, it's
I see. Interesting.
there's a funny history about this. One time our solenoid was broken, and then Atlas made a joke with us. They drowned the same figure with a line, making fun of us. Okay, so let's talk a little bit about the pixel detectors and the strips. So remember, the pixel detectors are in the very beginning of the detector, so they are the guys who stand with more radiation there. So you see, this is the pixel. If we compare with the gaseous detector, this is a person. Let's compare, for example, with this draw. This is a person, this is a gaseous detector. So they are really big, like this size. And this is the completely pixel detector that we have there. Even this is a very, let's say, lower size. It has 125 million pixels because they are very, very, very tiny due to the advance of the silicon pixel technologies. And as I said before, they are used to track the path of particles. And yes, we can precisely track this. We can do this. And this is ideal for short-lived particles because they are at the very beginning of the detector. If a particle is produced here and then it will die like here, we can detect using these guys. Because most of the particles will not go further than this. Oops. Okay, we have 4 layers here in this guy at what is it? 3, 7, 11, and 16 centimeters. We have 4 layers. And the surface area of this entire detector is 100 micrometers per 150 micrometers. And as I said before, if you take the innermost part, which is closest to the beam, we have around 600 million particles per square centimeter per second. So it's a really huge number of particles that passes through it. And also, there is a interesting thing that this guy is like an oven, because it has a power consumption of 7.5 kilowatts. That's why we need to put some cooling tubes to put this temperature down to operate this guy at a minus 20 degrees. And this is a normal silicon sensor, and see these are the pixels. Each of these detectors is a thing like this. So we have 125 million things like this in there. Okay, and then just after the silicon, we have the silicon pixel, we have the silicon strips that are just after. And then they are precisely the same detector, but instead of pixels, they are strips. So the resolution is not as good as the pixel, but it's very nice as well. Okay. And remember that at the beginning I show some modules. We have 15,200 modules of these guys here at the CMS. And this is how we install it there. Okay, now again your turn for you to play. So the first problem is about the semiconductor physics. So I again put 2 tables and ask you to do some calculations using the NI equation. And also I ask you to make a plot to see how we can vary the temperature and to learn how the concentration of holes and electrons will change or not. Okay, and then do the same for 0 Kelvin. Then the second problem is based on the aging of silicon detectors, because as I said, we have a huge number of particles, huge number of radiations, and then these detectors will suffer. So I ask you to calculate here to enumerate who will suffer more with depending on the radiation that you are applying on these detectors. And then 3, I ask you just to name what's the best semiconductor to measure tracking particles. I talk about this. And the last one is if you want to build a calorimeter, you choose a gaseous detector or semiconductor. So you just explain why you make this choice. Okay. These are the references. You can check here these books, and that's all.
Thank you so much, our guest. Questions here?
Maps, you said that the power consumption of the, I think was the silicon pixel detector was until was like over 7.5 kilowatts.
Yes.
And yeah, it's quite a lot. And I want to know if you think that it's possible to optimize the power and consumption and make it more sustainable to the experiment. You think that if the power consumption was optimized, the results will be related to, so you have some change in the results, or you think it's something possible?
Okay. At the CMS, we have dedicated groups that are working to upgrade and to improve the detectors. The fact is that the power consumption per pixel is very, very low. It's like 50 milliwatts. Oh. And then this is a matter of improving the pixel technology. So I don't know how is this technology is improving. Is not related directly to the particle physics. Oh, okay. So it depends on the evolution of the technology, you know. Oh, okay. But I know that we have groups that are working on the upgrades and the development of these detectors. But I don't really know if this is possible because they are very, very, very tiny.
Okay. Thank you.
More questions? No? Let me check the meet. I think we don't have questions, so see you later at 10 and 2 p.m. And please remember to sign the Google Forms there is in the site. We have fits the Google link there in the YouTube. Thank you so much. See you.
Thank you, guys.